Everybody all right? Okay. Can anybody tell me what we're talking about?
Rank and nullity.
Rank and nullity, right? Rank. So what's rank again? Let's recall. We're doing rank, nullity. Right? What is rank? See if you can remember without looking at your notes. Anybody know? Anybody remember without looking at your notes? It's like it's some sort of. You don't have to tell me exactly. It's this sort of thing that shows something or other. Yes.
Doesn't it have to do with the dimension of the rows?
Yes, the dimension. So you have a matrix, right? You have a matrix, and then you look at the span of the rows, right? And you look at the dimension of that. So it's the dimension of the row space of A, right? So you take the span of all the rows. That gives you some subspace, right? And you look at the span. You look at the dimension of that. And the nullity is a little bit more tricky. Maybe. What's nullity? Ava? No? Yes? No? Anybody have some sort of vague impression? Don't worry, you don't have to know everything exactly, right? But you want to have some sort of vague impressions, and then as time goes on, make them precise. Okay. So nullity has to do with the null space. Yes.
Is it the dimension of the null space?
Dimension of the null space, exactly. Right? Right. And remember, the null space is the stuff that gets killed by A, right? It's all the null space, remember, is defined to be the vectors wherever they are, such that AX equals 0. In other words, the null space is the solutions of the homogeneous problem. Okay, and then we ended with this thing, the rank theorem, that said that if you have an M by N matrix, M rows and N columns, then it's always true that the rank of A plus the nullity of A equals the number of columns, which is the number of variables in the corresponding system of equations, right? And the reasoning was that this thing on the left turns out to be the number of pivots, which is the same thing as the number of lead variables in the corresponding system. And this thing on the right turns out to be the number of free variables, again, in the corresponding system. And that's the number of lead variables plus the number of free variables is the number of variables, which is n. Okay. So that's where we stopped. We did a couple of exercises. Okay, so we commented earlier that you might be wondering why don't we care about the dimension of the column space, right? Why don't we care about the dimension of the column space? And the reason is that the dimension of the column space is actually the same as the dimension of the row space. So let's explain why. So the dimension of the column space of A actually is the same thing as the dimension of the row space, okay, namely the rank. Okay, so this one takes a little bit of thinking. So let me recall first that if you have two row equivalent matrices, then AX equals 0 and UX equals 0 have the same solutions. Right? The solution set doesn't change when you do elementary row operations. right? That's to say, the vector x satisfies the first guy if and only if x satisfies the second guy. I'm kind of saying the same thing. I'm not sure why I wrote it again, but anyway, it's the same thing. Okay, you don't have to write that. But here's the important part. Here's the key insight. So we're going to shift the view. Shifting your view, what that says is that any dependence between A's columns corresponds to a dependence between U's columns. Right? Because what that says is that x1a1 plus x2a2 plus xn equals 0, the zero vector, if and only if x1u1 plus x2u2 plus xnun equals 0. Right? This is actually kind of cool. So it says, like, if you take 1 of the first column plus 2 of the second minus 5 of the ninth column and you get 0, then that's going to happen with U as well, and vice versa. Any dependence between these guys, this guy's columns, must correspond to a dependency over here. Okay. Okay. So, let U be the reduced row echelon form of A. Okay. Now observe, any column of U that doesn't have pivots. Any column of U without pivots is expressible as a linear combination of those with pivots. Right? Let me give you an example. Right? Like, suppose I have this. Suppose this is the reduced row echelon form of some matrix. Okay. If you look at the columns that don't have pivots, right? That's this column and this column. Well, each of those guys is expressible as a linear combination of the ones with pivots, right? This guy is twice that guy. This guy is 3 of this guy plus 2 of that guy. Right? Is this clear? The columns that don't have pivots are in the span of the columns with pivots. Right? Further, the columns with pivots are linearly independent, right? Because it's 1 0 0 0 0 0 1 0 0 0 0. Right? Further, the columns with pivots are linearly independent. Okay. So what does that tell you? That tells you that the dimension of what does that tell you? That tells you that in the original matrix, the same thing holds, right? That the original last two columns are in the span of the first two columns, and the first two columns are linearly independent. Okay. Right. So, right? So the same holds for A, the original matrix. A. And thus, the dimension of the column space of A is just equal to the number of pivots in its reduced row echelon form. Okay, but the number of pivots in the reduced row echelon form is the same thing as the dimension in the row space of A. Right? So that's the rank. So the point is this, that if you take your matrix and you reduce it down to its reduced row echelon form, well, the dimension of the column space is the number of pivots. But the dimension of the column space, the dimension of the row space is also the number of pivots. And so the dimension of the column space and the dimension of the row space are the same. Okay. 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 Let me do an example that will bring it down to earth. Okay. Okay. So. Okay. Let's see. Okay. So we start off with a matrix. Sorry, I need my glasses. Okay. So we start off with a matrix. 1, 2, 2, 3, 2, 5, 4, 8, -1, -3, -2, -5, 0, 2, 0, 4. Then you do Gaussian reduction on it. It turns into this matrix. 1, hold on, -2, 0, -2, -1. Okay. 0, 1, 0, 2, 0, 0, 0, 0, 0, 0, 0, 0. Okay. Okay, so let me ask you this: what's the basis for the row space? What's the basis for what's a basis for the row space of A? Turn to a neighbor and talk, to say, and you can be like, I don't know. Anyway, turn to somebody nearby and be friendly. Step outside.
Oh, right. Well, it's like the bones. Oh, I don't know.
Okay.
Let me look at my notes. Do you know what I mean?
Wait,
So
do you remember something like
So like.
the row space is the
some
span
vectors that
of
you
the rows?
span.
Yeah, so it is the span of the rows. So basis or
Yeah.
span.
That's a good shot, I
Okay, anybody know what the answer is? Anyone want to say? People are smiling, but nobody's talking. Teo?
Theorized that maybe the basis could be the columns, like the transverse of the columns. as like
You're making it harder
or
than it
rows,
is.
or just like the rows.
It's just the rows here.
Yeah.
It's just the rows here, right? Because remember, right, when you do row reduction, you're not changing the span, right? When you're doing, we start off with the rows here, right? And then we do elementary row operations. Doing elementary row operations doesn't change the span. We do so many elementary row operations that we get down to this reduced row echelon form. We still haven't changed the span. And notice, these guys are linearly independent. So these guys are linearly independent and have the same span as this. So these guys are the basis for the row space of the original matrix. Okay. Does that make sense? Ask if it's confusing. Anybody confused? Okay. Right. So basis for the row for the row space is actually in this 1, 1, 0, 2, -1, 0, 1, 0, 2. Right? Why? Because elementary row operations don't change the span. Right? Why? Elementary row operations don't change the span, so we come down to here. These guys still span the same space, and they're clearly independent, and so they are a basis. Okay. Let me ask you another question. What is a basis of the null space? These are just sort of calculation things. How do you find the null space? Tim, do you wanna? You look like you know the answer.
Well, I guess if we go on the same sort of train of thought, we can find whatever solves the what was it called? Whatever.
The solutions.
Yeah, the solutions, and it should be the same.
Exactly,
Yeah.
right? Because remember, you haven't changed, when you do elementary row operations, you don't change the solutions, right? So recall, elementary row operations don't change the solution set. So we just solve it for this one, right? We say, well, this says x1 plus 2x3 minus x4 equals 0, x2 plus 2x4 equals 0, and that tells us that the solution must look like -2x3 plus x4, -2x4, x3, x4. Right, that this is the solution set. This is the solution set, and we can rewrite it. More simply as -2, 0, 1, 0 plus x4 times 1, -2, 0, 1. Right? So these guys are the bases, right? These two things are the bases. So what's the basis? What's the basis of the null space? -2, 0, 1, 0. 1, -2, 0, 1. Okay. And notice that the dimension of the null space plus the dimension of the row space equals 4, right? Rank theorem in action, right? These guys, this has no 2, this has a dimension of 2, that has a dimension of 2. 2 plus 2 is 4. 2 plus 2 is 4. I think that may be the first time I've said that in a math class. Okay, yeah, and I've been teaching for like 30 years or something. Okay, okay, the third question is the hard one. What is a basis for the column space? What's a basis for the column space? Okay, and for this, you want to think. So remember, right? Ax equals 0 if and only if ux equals 0. If a is row equivalent to u, then ax equals 0 if and only if ux equals 0. In other words, dependencies between the columns of A correspond to dependencies between the columns of U. Okay, so I'll be really impressed if somebody figures this out. So anybody want to try? If you don't get it, that's kind of what I would expect at this point. But anybody anybody get this well enough that you can tell me what would be a basis for the column space of A? That's okay. That's okay. Let me. I'm going to let you guys talk to each other for one more minute, please. Sorry.
If we like add a coefficient with, so like with the original, and then like set it equal to the reduced row echelon, and then like find like put it in sense. Like this would add up to 1, and like, or like this would be 7, so you like something like that. The coefficients.
Sasha, do you wanna say something?
I have no idea, but like
That's the right answer.
add the coefficients of the columns and like set it equal to find out the different ratios.
Oh, so try to use this fact about the dependencies. Like dependencies between the A's will correspond to dependencies between the U's. So let me explain what's meant by that. So if you look, right, so this fact turns into the statement about dependencies. Okay, right? What does that mean concretely? That means that, look, this guy minus twice this guy is 0, right? This column minus this twice of this column is 0, right? And if you look at the original matrix, this column minus twice this column is 0, right? So in other words, right, u1, 2u1 minus u2 is equal to 0, and that actually corresponds to a1 minus a3, sorry. a3 is the 0, right? Similarly, this guy is -1 of this guy plus 2 of that guy, right? This column is -1 of the first column plus 2 of this column. And if you think about it, you take -1 of this guy plus this plus twice this guy, you get that. -1 of this guy plus twice that is that. -1 of this guy plus twice that is that. -1 of this guy plus twice that is that, right? So this is what I mean by dependencies of, the dependencies stay the same. Okay, so what does that tell you? So you look at this thing and you say, well, look, in this world here, this is a base. These first two columns are a basis for the column space, right? This guy's column space, right? It's spanned by these two vectors. What does that tell you? That tells you that these two guys are actually a basis for this guy's column space. Okay, right? Because these two guys are in the span of these guys, because these two guys are in the span of these two guys, right? And these two guys are linearly independent because these two guys are linearly independent, right? If there were any dependency between these two guys, well, that would have been reflected over here. Okay, so that's the point, right? The basis for the column space of A is the corresponding vectors, 1, 2, -1, 0, and 2, 5, -3, 2. It's the vectors that correspond to the basis, the obvious basis for the reduced row echelon form. The basis for the column space A is the vectors, the columns, sorry, of A that correspond to the columns of the reduced row echelon form that have pivots. Right? These guys. Those guys. Okay. So all of this, you may be kind of shocked, but all of this just comes from this statement here, right? It just comes from this thing here, that the solutions of this guy, if A is equivalent to U, then the solutions to the homogeneous problem are the same. Turn to a neighbor and say, think, and try to formulate a question if you have a question. If you have a question. Because this is kind of the end of this section. Yeah, this is the last thing in this section. Anybody bold enough to risk a question? Yeah, Eva, great.
Why do we use like the reduced form of the rows for the basis of the row space, but we use like original form of the columns for the basis?
Yeah, that's a good one. And people often get this wrong. They'll say, this is the basis of the column space. This is the basis of the column space of the reduced row echelon form. But the trouble is that the column space of the reduced row echelon form is not the column space of the original thing. And very clearly, right? It's got nothing down here, right? There's no entries in the third and fourth, positions, right? So the thing is that when you do the reduced row echelon form, you don't change the row space, but you seriously change the column space. Okay, so during the reduced row echelon form, bam, the span of this is still the span of these two rows is still the span of these rows. Okay, and so these guys being linearly independent are a basis for the span of these rows.
We just prefer them because like they're simpler.
Prefer them? Wait. I mean, it would if you we get a basis, right? If you just have these four things, it's hard to see what the basis is, right? The question is basically find a basis for the span of for the row space, right? And so we wanted to find a minimal set of pairs that a minimal set of vectors whose span is the same as the original span, right? Yeah. Right. Okay. And then how do you get the basis for the column space? Well, you can't just take these guys, but you use the fact that the dependencies of this matrix are the same as the dependencies of this matrix, and so you say, well, look, these two columns are a basis for this guy's column space, so that tells me that these two first guys must be a basis for this guy's column space. Okay, so that comes from this observation. Okay. So yeah, so remember concretely, remember that how do you find the basis of the row space? You do the reduced row echelon form, and those are it. Okay. How do you find the basis for the column space? You do the reduced row echelon form, and then you take the corresponding columns back here. Okay. How do you find the basis for the null space? Well, you do the reduced row echelon form, and then you have to do a little bit of work and then figure out what the basis for the null space is over here. Okay. These three things are things that we're going to use a lot. Okay. So be sure that you know how to do them. They'll be quite important in 2 chapters from now, when we start talking about eigenvectors and eigenvalues. Okay, so yeah, that is the end of that. Okay, so yeah. Okay, so now in some sense, we're going to head into kind of, I think, what could be called the real topic of linear algebra. Okay, the real topic of linear algebra are these things called linear transformations. Linear transformations. And they are things that, usually you write them as T for transformation. They're things that go from one vector space to another vector space. Okay, so they take in a vector and they give you back a vector, right? They take in a vector and then they give you back, some other vector. Some other vector in some other vector space. So this may seem kind of abstract and all, but keep in mind that matrices can be used as linear transformations, right? You give it a vector, and then it gives you back some other vector, right? You take a vector and you hit it with a matrix, and it gives you some other vector, right? That is actually a linear transformation, right? It's something that you give it a vector, and then it gives you back some other vector, right? And that vector could be in some other space, right? Like if this is n by n, and this is n by 1, then this guy's in n by 1, right? So that this guy, this mapping goes from Rn to Rm, right? It goes from one vector space to another vector space. Okay, so don't be intimidated by this. Always keep in mind that this is the basic. The basic idea behind it is basically is left multiplication by a matrix. Okay. Okay. So maybe let me start it off in that way. So let's think. Consider a matrix, an n by n matrix. Okay. And define T sub a, which will be a function going from Rn into Rn. Okay. Define it by saying T sub a of a vector is just a times that vector. Right? So T sub a is sort of like the left multiply by a function. Okay. Now observe. If I'm looking at T sub a of a sum of vectors, well, what is that? That's going to be a times the sum of vectors. Right? Well, that's AV plus AW. Right? By, because this multiplication distributes. Right? But AV I can rewrite as TA of V plus TA of W. Okay. Second thing I want you to observe is if I take TA of V and then I multiply V by some constant alpha, what happens then? What do I get then? Yeah, Eva.
Alpha TAV.
Alpha TAV, right? Right, because I get alpha AV, which is the same thing as alpha, I get A alpha V, which is the same thing as alpha AV, which is alpha T sub A of V. Right? Right, so, what's the point? That this mapping works well with addition, and it works well with vector addition, and it works well with scaling multiplication, right? If I've got two vectors in the domain, and I add them together and I map them over, I might as well have mapped them over individually and then added them afterwards, right? That's what this is saying. I add them first, and then I send them through the function, or I send them through the function first, and then I add them later, and I get the same thing. Similarly, right? I take the vector and scale it, and then run it through the function, or I run it to the other vector space, and then multiply it by the scalar. It get the same thing. Okay. So these two things together are called linearity. Okay. That if it behaves well with respect to vector addition and scalar multiplication, so i.e. behaves well with respect to vector addition and scalar multiplication. So what we're going to do is we're going to abstractify that. Okay, we're going to take that and then turn it into an abstract definition. And we'll say, suppose we have two vector spaces. Okay, and we have a map from one vector space into the other vector space. Okay. If T is linear, in other words, T of V plus T of V1 plus V2 equals T of V1 plus T of V2, and T of alpha V equals alpha T of V, then we call T a linear transformation. From V to W. Okay, but always keep in mind that you have this sort of prototypical example. Left multiplied by a matrix. Right? Left multiplying by a matrix is a linear transformation. Okay. Let me show, so this is not in the order I normally do it. This is example number 4. But just to show you something cool, consider differentiation. Okay, so like the derivative operator, right? ddx, say. Okay, and suppose that let V be polynomials of degree 3, say. Okay. If I take one polynomial and add it to another polynomial and then differentiate it, is that the same thing as the derivative of the first polynomial plus the derivative of the second polynomial? Yeah, absolutely, right? Okay. If I take a polynomial and multiply it by a scalar and then differentiate it, is that the same thing as the scalar times the derivative of the polynomial? Yeah, absolutely. Yes. Right? So ddx, differentiation, is a linear transformation. Okay. So this is sort of like a change of perspective. It's saying that these things that we've been doing, mapping, going from one vector space, from one vector space to another space. Actually, there are a lot of things that behave like that. And so we're going to make a more general definition and consider these objects called linear transformations. Let's see. Let me do example 3. So T sub theta going from R2 to R2, which is rotate clockwise, say, or counterclockwise by angle theta. Okay. Is this linear? Is this a linear transformation? It's going from R2 to R2, from one vector space to another. If I have, let's do the second one first. Suppose I have a vector and I scale it by some constant, and then I rotate it by theta. Is that the same thing as if I rotate it by theta and then scale it by that constant? Sure. So part 2 is satisfied. If I have two vectors and then I add them together and then I rotate them, is that the same thing if I rotated them first and then added them together? Yeah, same thing. Okay. So yeah, so this is also a linear transformation. Okay. In fact, it actually corresponds to left multiplication. It's the same thing as left multiplication by the matrix A, where A is cosine, sine, negative sine, cosine. Okay. In fact, there's a matrix that left multiplication will do the same thing as that, using by left multiplication. Let me do one. Let me do one more example, just to make everything backwards. Let's go again. We have a map from R2 to R2, and the map is you take x, y, and then map it to x comma 0. X, y goes to x comma 0. Okay, so pictorially, what that does is you have your vector xy, and then it gets mapped to x comma 0. Okay, it's what's called a projection. You project the thing onto the x-axis. Okay, is this a linear transformation? Is this a linear transformation? To check something is a linear transformation, you need to check is L of one vector plus another vector equal to L of one vector plus L of the other vector. You need to check L of alpha v, is that equal to alpha L of v, right? So like if I have a vector xy and I scale it by alpha, is that the same thing as alpha times L of xy? Check. L of alpha x, L of this thing, well, that's going to be just alpha x comma 0, right? What about this thing? This thing becomes x comma 0, and then you hit it with alpha, it becomes alpha x comma 0, right? So that's true, right? For the first one, if I have L of let's say like alpha beta plus delta gamma. Let me just use letters. A, B, C, D. If I take L of a sum, is that the same thing as sum of L applied to each of those guys? Yeah, right? Because here you're going to get A0, here you're going to get C0, and so you get A plus C comma 0. And here you get A plus C, B plus D, that gets mapped to A plus C comma 0. Right? Right, so yeah, this is also a linear, this projection guy, also a linear transformation. Okay, and if you think about it, it corresponds, this L actually corresponds to left multiplication by 1, 0, 0, 0. Right, because when you multiply x, y by 1, 0, 0, 0, you get x, 0. Karshel.
So are all linear transformations, they need to be able to be represented as a left multiplication?
You get 2 points on the exam for that.
Okay.
Great question, really good question. And the answer is yes. All linear transformations, well, but then you might think, what about differentiation? That's what you're going to say.
Yeah.
I'll give you another point for that.
Okay.
What about differentiation? Differentiation is, what matrix do you say, I'm going to hit this polynomial with a matrix? Right? That doesn't make any sense, right? What we're going to do is see that so differentiation goes from order 2 polynomials to order 1 polynomials. What we're going to see is that every vector space can be sort of made identical with a corresponding Euclidean space. Okay, so that, right, so the polynomials of degree 3, as you might expect, we'll use our coordinate vectors. We'll put coordinate vectors on it, and then basically represent it as two numbers. Well, that's R2, right? We'll take our abstract vector space and represent it, using coordinate vector here, right? And so there'll be a matrix here between these guys that does the same thing, that does the analogous thing that differentiation does over here. Yeah. So that is going to be that's what most of this chapter is about. Initially finding, given a linear transformation, giving a linear transformation from Euclidean space to Euclidean space, finding the matrix that does it. That's going to be really simple. And then 2, doing that same thing between abstract vector spaces, and that'll involve doing this sort of business of identifying vector spaces with Euclidean spaces. So that's going to be kind of tricky. This is, I think, maybe the hardest chapter in the book. So read up beforehand, and let me think. Where does things get hard? In the next section. So yeah, so 4.2 is really the tough one. So yeah, but after that things become a bit more straightforward, I think. Yeah. Okay, sorry to keep you over. That's it.